Data provenance, curation methodologies, and alignment protocols have overtaken raw GPU cluster size as the primary determinants of final model capability. The engineering of the data supply chain now dictates the absolute limits of the software. The pre-training phase instills foundational linguistic competence by ingesting datasets exceeding 15 trillion tokens. This process transforms a randomly initialized neural network into a base artifact capable of basic syntax and world knowledge. This intersection represents the data wall. Predictive models estimate that the total supply of publicly available, high-quality human text will be exhausted between 2026 and 2032, forcing developers away from the open web and toward proprietary archives. Large-scale platforms are accelerating this shortage by enclosing their data. Networks like Reddit and X have transitioned from free open APIs to enterprise tiers designed to monetize the human dialogue required for model training. On X, the economic impact is immediate. Passing the 2 million read threshold triggers a requirement for enterprise contracts starting at $42,000 per month, turning social data ingestion into a major capital expenditure. The era of the free internet commons for AI research is over. Raw data is now a guarded, enclosed asset class that determines which organizations can afford to develop frontier models. Ingesting the raw web is not a volume game. Much of that data is actively harmful. Without filtering, models absorb boilerplate text, toxic biases, and non-language hex dumps that destroy performance. Engineering teams use token distribution Kullback-Leibler divergence to clean the intake. This mathematical filter identifies and discards base 64 encodings and gibberish that evade standard dictionary checks. To prevent memorizing documents, developers use locality-sensitive hashing. Mapping sequences into reduced signatures allows systems to calculate Jacquard distances and remove near duplicates from massive datasets. This deduplication forces the network to generalize patterns rather than rote memorizing sequences, ensuring effective zero-shot reasoning. Once cleaned, the mixture of data domains must be optimized. Selecting the precise proportion of mathematics, executable code, and academic literature determines the model's eventual logic limits. The 42% math and code mixture utilized in Llama 3 built the structural reasoning pathways before the model ever saw a human instruction. By balancing these domain weights during pre-training, engineers mathematically set the zero-shot reasoning ceiling of the base artifact. Post-pre-training, the model is a passive next token predictor. It must be transformed into an active agent through supervised fine-tuning. Dataset quality is now exponentially more valuable than volume. According to the less is more for alignment hypothesis, or LIMA, fine-tuning serves a superficial role. It teaches the model to select a specific sub-distribution of its existing knowledge to match the tone of an AI assistant. This empirical comparison shows the power of curation. A model tuned on 1,000 high-quality, expert-written pairs comprehensively outperformed an equivalent model trained on the 52,000-sample alpaca dataset. Conversely, low-quality data actively pollutes the pre-trained weights, leading to factual errors. This makes human experts the primary bottleneck. Sourcing high-fidelity logic demonstrations for law or programming costs upwards of $75 per hour, quickly scaling the cost of a curated dataset into the tens of thousands of dollars. SFT data quality acts as the absolute ceiling for accuracy. Raw compute volume cannot compensate for a training set that provides flawed behavioral demonstrations. How do developers scale complex task diversity, like cybersecurity planning, without the massive expense of human subject matter experts? They utilize synthetic data generation. Pipelines like Instruct use existing frontier models to automatically generate diverse, progressively complex instructions from a small pool of human-written seeds. This branching tree illustrates the Evolve Instruct algorithm. A simple security request is algorithmically mutated into a multi-layered cybersecurity scenario. This automated expansion drops the unit cost of specialized instruction pairs from $50 down to $2. These pipelines leverage the reasoning of legacy models to forge new, complex pathways that would be economically unviable to source from humans. While data sourcing is a software challenge, the actual execution of weight updates is governed by strict physical hardware constraints. Updating model parameters using the AdamW optimizer requires the hardware to store 5 distinct matrices simultaneously in mixed precision training. This stack represents the model weights, master copy, gradients, and 2 momentum states, requiring 16 bytes of VRAM per parameter. For a 30 billion parameter model, this mandates 480 gigabytes of VRAM, requiring an 8-way H100 enterprise GPU cluster. This hardware barrier forces engineers to use parameter-efficient fine-tuning. By freezing the majority of the weights and injecting small matrices, they can update the model on a fraction of the memory. Following fine-tuning, the model undergoes alignment. This stage uses preference data, where an annotator ranks a chosen response over a rejected one to mathematically reward safety and corporate compliance. Historically, reinforcement learning from human feedback required 4 separate models to run in memory simultaneously: the policy, the critic, the reward model, and the reference model. Direct preference optimization disrupted this pipeline by collapsing the process into a single supervised learning step. The DPO loss function bypasses the reward model entirely, optimizing the policy directly on preference pairs. A KL divergence penalty prevents baseline deviation. Eliminating reward and critic models halves hardware needs, allowing local workstations to perform alignment previously requiring massive cloud clusters. To solve the human preference bottleneck, organizations use reinforcement learning from AI feedback. Frozen frontier models act as trudges, scoring millions of synthetic outputs thousands of times per hour. This shift toward algorithmic efficiency turns alignment from a compute-bound hardware problem back into a data curation challenge. Transforming a generalized model into an industry expert requires continual pre-training on proprietary corporate archives and unstructured data. This ingestion carries extreme legal liabilities. Anthropic's $1.5 billion settlement over the use of pirated books from shadow libraries proves that the financial risk of illicit data far outweighs the cost of legal licensing. Privacy regulators are applying similar pressure. Rulings against unauthorized scraping in Canada and cases against Clearview AI have established that publicly available information does not grant an automatic right to algorithmic training. To mitigate this, developers use proxy LLMs to execute named entity recognition. These local systems identify sensitive PII and replace it with statistically realistic synthetic surrogates, preserving the semantic utility of the data without violating privacy laws. As foundational generative models commoditize, the true economic value is rapidly shifting towards exclusive, legally secured data moats. For specialized legal and medical AI, the proprietary data integration now represents the majority of the system's market value. Once deployed, static weights are connected to live vector databases via retrieval-augmented generation to ensure the model's answers are factual and up-to-date. These managed vector databases introduce their own economics. Serverless platforms often charge based on RAID units, meaning query costs can scale linearly and punitively as the dataset grows. When ingesting massive retrieval results, models suffer from context confusion. Contextual retrieval architectures solve this by using an upstream LLM to inject global metadata into every document chunk, preventing the model from conflating similar concepts. Running these long context RAG windows imposes a physical VRAM floor. Maintaining the dynamic key-value cache for thousands of tokens mandates a minimum of 24 gigabytes of high-bandwidth VRAM for enterprise deployment. From the initial web scrape to the final retrieved vector, generative AI is a hyper-optimized data supply chain. Every formatting choice and curation strategy dictates the physical hardware constraints and final capabilities of the intelligence.